so just before I begin, a couple of little things to say. Details for the lab report, I'm going to send them to you by email right after class. Essentially, the important points of it are due in 1 week. And not a full lab report, it's there. Okay? The details will be posted for you on the 1 week. Okay? That's the first thing. Second thing, okay, so now we're entering what I consider to be like the top parts of electricity and magnetism. Today we're going to take it easy still, but this topic is what's the topic that's going to be the topic that's going to become our next topic. Alright, so I need you guys to get your A game. Try to pay attention, try to answer the questions if you can. I want to see you guys thinking about it. Okay? If you're wondering about the math, we're about to do some integrals. Not today, but next class. Okay, so between today and next class, brush up on it a little bit. We're not going to start out really hardcore, but it is going to get pretty tough. Especially since now we've added the layer of physics to it. It's going to be, not going to be that easy. Worst case scenario, right? This is if you really don't understand anything that's going on with integrals and things like that. It's one question on the test. You might not do well enough on question. Put your eggs in the other baskets and try to do well on those. Okay? It's not the end of the world. It's something that you need to know for this course for sure. So I can't not test it on you for you. And but like I said, it's a minor part of it. Okay? Good? No one still have the balloon not popped? All right. So here we are. This is a balloon that we're going to just work with. Today we're going to talk about something called electric fields. And electric fields is very similar to another concept that you're very familiar with. I'll get into that in a second. But I just want to ask you guys a question first. If I were to rub this under a shirt, all right, and put this here, am I going to, is there anything happening over here? Or is there nothing happening? All right, so let me go around my desk so you can see better. Right, so is there anything that's going on down here, or is nothing happening because there is no other object? What do you guys think? Something or nothing? That's my question. Something, absolutely something. Let me ask you another question. If a tree falls and no one's around to hear it, does it make a sound? Based on physics. Yeah, that's why scientists are better than philosophers. Don't tell yourself that. Absolutely, it makes a noise because it's the vibration of air molecules, et cetera, et cetera. All right. Now, because nothing is happening here, doesn't mean that nothing is there. Just because you can't see it doesn't mean nothing is there. A force is between two things, right? So that would be this charged molecule, this charged balloon, and then be another charged particle down there, and there would be a force between them. There is no other charged particle, so there is no force, right? I agree with you, there's no force, but there is something there, all right? Because if I did put something there, something would happen to it. Okay, do you guys get what I'm saying? That something that's happening there is called an electric field. That's what we're talking about today. If I were to leave this pen, if I were to let go of this it goes along the pen. And I said, there's no gravity right here. Yes, right? There's no force of gravity because nothing is accelerating. Right? Remember, force is like acceleration. There's no force of gravity. It doesn't mean that gravity is not here. What we're in the presence of right now is a gravitational field. Okay? All right, let's get started. Is that concept okay to you guys? Yeah? Okay. So that's what the electric field is. Learning objectives are going to be for you to understand the direction and how to computate the electric field. Next lab that we're going to do is called mapping electric fields. It's actually a fun lab, but it's quite long. But it's a fun lab. You have to draw like a topographical map of an electric current. It's actually quite interesting. We're going to do some of that today, but in a very basic way. Okay, so I got a joke for you guys. I'm a dad now, so I can make dad jokes. So just take a read of that, and I'll post the punchline in 1 second. All right. The the joke is if you don't, everyone gets it. Okay, good. All right. Okay. Aside though, next to the joke, there is a picture, the less of a joke, that is of two charges. Now there is a red charge and a blue charge. I mean, I'm telling you right now, in about 10 minutes, you'll understand which one's which. You'll be able to determine which one's which. But I'm telling you right now, the blue one is a positive charge, and the red one is a negative charge. And there are these lines that are leaving the positive charge, right, and entering the negative charge. And and there are these little arrows. What do those arrows remind you of? What did you maybe have done 3 or 4 years ago that might remind you of that? Yeah, magnetic field. Did you guys ever do that? There's like a plastic thing that you just put in a magnetic field, and all the arrows all of a sudden point in a certain direction. That's kind of what's going on here with these arrows here. If there are arrows involved, what does that tell you about electric field? What do arrows dictate? Carly? So there's a direction, and if there's a direction, then it's called a vector, exactly. So electric field is a vector. Okay, and we need to understand that. Okay, so we're going to have to apply our knowledge of x and y and all that stuff in this case as well. So here's what I mentioned. So a mass creates something called a gravitational field. A charge creates something called an electric field, and you'll learn in the second half of this course that a magnet causes something called a magnetic field. And they're all really the same. They're all vectors, and therefore they all have a direction, they all have a magnitude. Okay? We're good? Give you a couple seconds to write your notes down. Sorry. All right. So moving forward, I did mention to you that there is a direction to this, and we're going to talk about that a little bit here. But before we do that, I want to draw it's not really an analogy, it's actually just an equivalence. All right, so here we have a charge. All right, here we have a charge, and it's positively charged, this yellow ball, and we have this electric field going outwards. And again, remember that we, convention-wise, write it so that the field always leaves a positive charge and enters a negative charge, okay? Again, I'll mention that in a second, but that's why it's pointing outwards in this case. On a gravitational field, so for example, around our planet, we have a gravitational field, it's pointing which direction? Inwards, right? Because if something were to fall, the force is always going to be downwards towards the planet, unless there's a more massive object closer to us than our planet, but that's not it. So here I'm going to go downwards, and here I'm going to say away. All right. So here it is. The positive charge and the negative charge. So far, so good. Everything is super easy. There is these faint blue lines on the whiteboard here that I can't erase. Please don't get confused by that, okay? So these white lines, these blue lines, they're actually on the whiteboard. That's not a part of this yet. Okay, so this is an isolated positive charge. What I mean by isolated is that there's nothing else around it, right? And if there's nothing else around it, this is what the field looks like around a positive charge. And this is an isolated negative charge, and this is what the field looks like around an isolated a negative charge, okay? So there's nothing else around it, so that's the charge, that's what the field looks like around that charge. Anybody? Is the electric field real? This is my philosophy question. Does it exist? Would I teach it to you if it didn't? Of course it's real. What if there's a lone charge? What if there's just one charge in space? Does that one charge produce an electric field? Yeah, as long as it has a non-neutral charge, electric field automatically. So yes, of course. So here we have a charge. Can you guys tell me if this is a positive charge or negative charge? Positive charge, yes, because what? Ooh. Because what? It's going outwards, exactly. All right, and you can see that they're going outwards. I want to ask you guys a question now, and bear with me while I draw many of these lines. I want you guys to do the same thing if you can, because there's a note to write about this. Don't pay attention to the length of the arrows. I'm just not perfect at drawing that. All right. Where in this drawing do you think that the electric field is the strongest? Where? Right near the charge? You guys agree with that? So my question was, where do you think has the strongest electric field? Zach says right near the charge. Anyone disagree? Good, I agree as well. That's where there's the strongest charge. That's right, that's where there's the strongest charge. The strongest electric field. Now here's how we know. You judge the strength of an electric field based on, when we're talking about it schematically, obviously, based on the density of the arrows. Okay, so where are there a very dense amount of arrows? Look how close together the arrows are there. Do you guys see that? Right? And look how wide apart they are out here. So if these were the only lines that were present, I mean obviously there's more, and right next to it, the lines are closer together, therefore this field is stronger. Okay, take a minute to write that down. That's going to be important. Okay? So I'll repeat that for you guys. The closer the electric field lines are together, the stronger the electric field. All right. Let's move forward. I'm going to have more to say about this. Notes on the lines having to be positive are going outwards on a positive charge, and once the number of lines leaving is proportional to the magnitude of the charge and also the magnitude of the field. So let's write that down. It's proportional to the magnitude of the charge and the magnitude of the field. Just while you guys are writing that, I'm going to remind you that Tuesday is a Monday schedule. So we see each other on Tuesday. We're going to be in the room for that downstairs room there, that circular table. Okay? Yeah. Positive. Plus VE is positive, negative VE is negative. That's just kind of like a shortcut abbreviation kind of thing. Here I wrote down a note that's quite important. I wrote down that electric fields cannot cross. And that's super duper 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 important. The question is why? I'm going to ask you guys a follow-up question to answer that question. So I have a positive charge here and a negative charge here. I'll make it a positive charge. So two positive charges next to each other, all right, and I have my electric field going outwards. So I have my positive charges. Each one of them has their own field, all right? And the field exists. The field that exists is stronger at the center, but it exists everywhere, right? So if you're this far away from it, you're going to experience an electric field. The electric field might be smaller, but you still experience an electric field. Now, if I put a negative charge here, all right, where is it going to go? What is it going to get attracted to? Is it going to get attracted to that or that? These are the same exact charges. What do you think, Zach? Going to get attracted to both of them? So does the electron split and go half in each proton's direction? Or does it go to like an average direction? All right, so Zach says that it's going to go downwards. Okay. That's probably what's going to happen because it's not perfect. But if it were perfect, what would happen? What's that? It would what? Split up? Nope. Electrons can't get split. They require an enormous amount of energy. So what is going to happen to this electron if this were a perfect situation? So these guys are totally right here. Maybe I'll do it this way. If I have it this way like this, right? Where is this electron going to go? If the electron's right in the middle of these two totally equal charges, what's going to happen to that? Can do what? It won't move. Exactly. It will remain stationary. If it remains stationary, that means it's not feeling an electric field. All right. So if lines cross, you would have this electric field line going like that and this electric field line going like that, which means that the lines are crossing and therefore something would happen to it. But in fact, what happens is there is no electric field there. All right. So here, the electric field is actually going to go like this. And the electric field here is 0. Okay? All right. So moving forward, here's some important facts about it. All right. The direction of the electric field is determined by something called a test charge. A test charge is a proton. Okay. Remember this. A test charge is a proton. And I was saying, if I placed a, let's go into the slide over here. If I placed a test charge there, all right, a positive test charge there, because the test charge is always positive. If I place a test charge there, would the positive charge go away or towards the center of that charge there? Where is that? Which way is it going to go? Away, yeah. Cedric is right. It's going to go away. So that's how we determine, that's not how we determine, that's how we establish the direction of the electric field, all right? The electric field exists, right? And we determine its direction, or we kind of explain its direction by saying, what if there were a positive charge there? Which direction would it go? Okay? And in the case of that, in the case of a positive charge, that test positive charge is going to fly away, and the negative positive charge, the negative test charge, which is still a positive charge, is going to go, it's going to get attracted to it. So that's why it's inwards for a negative charge and outwards for a positive charge. Okay? There's a statement here that says the amount of force per test charge. This is the most important part of this slide. I'll ask you guys a question. Okay. I bought 12 bananas for $6. How much was each banana? How much? 50 cents? Yes. You can say that a bit more confidently because now you're in CJEP and you can do this. All right. So 50 cents per banana. Now that's the same thing as what a force is to electric field. That just sounds the most ridiculous, silly thing ever. Because what I'm trying to say is, let's say you have 12 newtons of force acting on 6 coulombs, right? What is the electric field? Well, the electric field is 0.5 newtons per coulomb. Okay, that's what electric field means. It's the rate of the force per test charge per 1 coulomb. All right, so that's where this test charge comes into play. Okay, you understand my analogy? I hope that makes sense. Now let me ask you a question. If I had force, because we did a lot of problems on this, and you guys have a quiz on this next time. We did force, which is KQ1, Q2 over R squared. We determined that force is the attraction or the repulsion force between two charged objects. All right. In this case, whenever I'm drawing an electric field, am I drawing another charge, or is it just one charge? It's just one charge, right? So there isn't a Q1 and a Q2, it's just a Q, and the Q is the thing that we're focusing on. So if I were to talk about electric field, which is the symbol E, you guys can write that, we're both vectors, so put your arrows over it. If we're talking about E, which is the electric field, it's basically, well, F divided by Q, right? Or I'm not going to write which Q, but F divided by Q, because that's what I did here, right? There's 12 newtons divided by 6 coulombs. That gave me this 0.5 newtons per coulomb number. I did that, right? I did force divided by Q, which means that if I take this, Q1, Q2 over R squared, and I divided it by Q, I can cancel out one of the Q's. And the Q that I'm canceling out is the one that's not the one that I'm finding the electric field for. So I can do something like that, and I'll end up with electric field equals to KQ over R squared. And this Q is the thing that I'm finding the electric field for. You have a hard time seeing? I'm going to have to write here. E equals F over Q, which is equal to KQ1, Q2 over R squared. You can cancel out this Q and that Q. Yeah. It doesn't matter which Q. The point is that you're going to be left with one Q. Okay? All right, so got a question for you here about directions and all that stuff. What is the sign of charge A? Positive, yeah, very good. That one is easy. How do we know that? The arrows are going out of A. Okay? I have a second question for you. This is a bit tougher. So compare the magnitude of the electric field at point A compared to point B. Which one is higher? Did you have an answer? B? Anyone else? Who has a higher electric field, A or B? And remember, A and B aren't charges, eh? They're just places, right? So is the location A have a stronger electric field, or is location B have a stronger electric field? What do you think, Zach? B? Okay. I'm going to play devil's advocate here because you guys both said B. Anyone else think A, by the way? Might be right. Why do you say B? Why do you say A, Samantha? Ah, okay. Anyone else? What if I were to say this, which is a totally valid argument, all right? And you guys will determine if my argument is correct or not. If I were to say that this is a positive charge right there, and there's a negative charge right there, right? And I have my arrows going from positive to negative, right? Because they leave the positive charge, they enter the negative charge, so you can make that all into one line. And there's other ones that are doing this, and doing this, and doing this, and doing this. Which one of these lines, which one of these points, is going to be closest to my charge? Because remember, my expression for electric field is kq over r squared. So the less the r is, the lower the r is, the distance from the charge, the higher the electric field is going to be. So if I were to draw it this way, which one would be higher? In this case, A would be higher. But is that necessarily the case? What do you, how can I phrase this? Okay, so let me erase this right here. Okay. So if I were to erase this, why did I decide to put my positive charge where I did and my negative charge where I did? I decided that I was just arbitrarily going to put my positive charge there and negative charge there, or why did I do that? Right. Could I have put my positive charge there and my negative charge there? Would that be right, less right, or utterly wrong? What's that? What do you notice about this line here? It's straight. Okay, so whenever you have a positive and a negative charge, then the first thing that's going to happen is going to be a straight electric field line between the two. All right, that's the closest point between them. That's where it's going to be the strongest electric field. So I want to reveal it to you guys now. A student in group 2 was saying that if this is a straight line, that means there must have been a positive charge here and a negative charge here. Very good observation. All right, amazing. However, it doesn't tell us anything about the rest of it. All right, so it's possible. Whoops, just remove this. It's possible that I also have plus charges all along here, right? Because these lines are pretty close to being straight, and the negative charges are on here. And there's just that this one is the strongest and this one is the strongest. I don't know what the case is because I never drew the charges. You can't tell me where the closest place is to the charge because I didn't draw the charge. All right, and therefore the original answer that Zach and who is it? And Gabrielle came up with was correct. Right? The answer is B. The answer is B is stronger than A because the lines here are closer together than here. Number one, that's evidence that we do have. We have no information about where the charges are. But I have to give credit to that statement though, because it was the person who came up with it. It was Azam, by the way. He comes up with really, really cool stuff. Actually, I love the way his brain works. He came up with that theory, and I think it's a totally valid explanation. But it's unfortunately there's just not enough information to be able to confirm it. Are we good? So we talked about this. It's an electric field is the force acting on a test particle, which is 1, right? So if I were to write it here, I could say that it's 0.5 newtons per 1 coulomb, right? So it's per coulomb. And that's what a test charge is. It's positive 1 coulomb. Okay? So we talked about that here. that we have this test charge near an object. And when you put this test charge near an object that's charged, you're going to feel a force proportional to its charge. And if it's a test charge, then it's the same value as the electric field. Okay. So there's that relationship that we talked about on the whiteboard, right? So E is equal to F over Q naught. I wrote something, an equation here that you might not be familiar with, but in fact you are very familiar with it. I wrote it on the board there. What you're not familiar with is this value here. And what you need to know is that that value, 1 over 4 pi epsilon, is equal to K, right? Epsilon is the permittivity of free space, in case you're curious. You can look that up and what that means. Even I don't even know what that means. Yeah. Correct. So this here, if you notice, this is a Q naught, that's referring to that charge, and this is a regular Q, and that's referring to that charge. Yeah, so if we were to talk about forces, this would be Q1 and Q2. All right, but because we're talking about electric fields, we only really care about the electric field around this one. So that's why we have that in the formula. That's a good question. Here's a summary of that. So a charged particle creates an electric field. The direction of this field direction is in the force of a positive test charge. So there's an example of that. And it's similar to gravity in the sense that the further away you get from this charge, the weaker the electric field gets. Okay? That's what that says here. So if you double the distance, you get 1/4 of the electric field. If you triple the distance, you get 1/9 of the electric field. How did I get those numbers? Zach? Yeah, it's 1 over 2 squared or 1 over 3 squared. Okay? So Alex, I'm looking at your screen here. There's a little bug here. It looks like you don't have the ability to put an arrow there. So that symbol is supposed to be a vector arrow. Oh. Yeah. Let's answer this one together. It's going to require you to calculate something for me. So I have here an electron, right? What is the charge of one electron, by the way? Yeah, is that? Yeah, 1.6 times 10 to the negative 19, exactly. What are the units? What are the units? Coulombs, yeah, okay. So here I have a charge. It's an electron. It's just one electron. So I'm asking you, what is the electric field at this point here? Okay. So first of all, tell me, is it towards the left or towards the right? What is it? Towards the right or towards the left? The electric field at this point, what is it? I need more people answering. Come on, guys. Cedric says to the right. Why did you say to the right? Oh, sorry. To the left? Do you think it's going this way? So Cedric says to the left. Anyone agree or disagree? Kevin, what do you think? Left? Why did you say that? Maybe Kevin, you want to answer? Why do you agree? Electric field is negative. Ah, okay. So it is to the left because it's a negative charge. Here's our first answer. My second thing I'm asking for is not quantify it for me, please. Tell me what is the value of the electric field in this. Okay? So we have everything we need. We have K, because that's a constant that you know. You have Q, which is written right there. You have R, which is written right there. By the way, do you guys know what this number is? What 1 times 10 to the negative 10 is? There's a special name for that. It's called 1 angstrom. It's an A with a knot over it. We measure a lot of biological protein distances with this unit called angstrom. Okay, 1 times 10 to the negative 10. Oh, more knowledge. The more you know. So yeah, please calculate the electric field for me. It should give you a number. Anyone have an answer for me? Who? Yeah, Isabel? What? And what are the units? We talked about it when we were talking about the bananas, remember? Yeah, newtons per coulomb. Okay, this is huge. Huge, huge, huge. 1.4 times 10 to the 11. That's 140 billion newtons per coulomb. That means if I put a 1 coulomb charge there, what force will it feel? It would feel 140 or 140 billion newtons of force if I put a 1 coulomb charge there, all right? But that makes sense. Look how close it is to the charge, all right? This distance is really close. And if you're that close to a charge, then yes, you're going to feel a huge amount of force. If I were to take this distance and say it was 1 meter away, then this would be almost nothing. What would, so just, if you can, Isabel, real quick, repunch it in and tell me what the electric field would be at 1 meter away from an electron. It would be like something times 10 to the negative 10, I imagine. Something to the negative 9, right? So we went from 140 billion newtons per coulomb to 1.4 nanonewtons, which is like nothing. Yeah. The negative sign will tell us which direction it's going. Yeah. What I'm asking you, it's a vector, so you can tell me that it's negative 1.4 times 10 to the 11 newtons per coulomb, or you can tell me 1.4 times 10 to the negative coulomb newtons per coulomb to the left. Yeah. Exactly. Exactly. Yeah. Yeah. So that was the question that Kevin had. The question was that the answer was that it all depends on the direction. You can tell me the negative sign of it as long as you know that means to the left. Okay? To me, the direction is more important than the sign in front of it. Okay? All right, let's move forward. We said that the direction is to the left. We figured out what the direction was. At point C in this case, so here we have two totally equal positive charges. At point C, what is the electric field going to be in this case? We talked about this. 0, right? So the answer is 0. The reason for that is because the electric fields cannot cross. And so therefore, when these guys get too close together, they're actually going to go do something like this. All right, so at point C, the electric fields totally cancel out. There's another way of doing it. So if I were to erase this, what is the electric field at point C, right? What is the electric field here? If only the left charge existed, if only this positive charge existed, what would be the electric field at point C? So ignore this now for now. It would be this direction. Okay, so Karali says here, she is right. All right. And what about if this one didn't exist and this one is just acting on it? What would the direction of the electric field be? Zach, to the left? Yeah, you're also right. Would it be the same magnitude as this one? Yeah, okay, so now if both existed, those vectors cancel each other out, and therefore there is no electric field acting on it. Okay? I'm changing up the problem. Sorry, I'm going a little bit fast because one, you guys look tired and I want to get you guys out. And two, we're also running out of time a little bit. All right. I'm saying now this time that the positive charge, the blue one, is stronger. So what is the direction of the electric field at C? What do you think, Zach? To the left? Naomi, you say to the left? Everyone agrees? Yes, because there's a stronger field to the left compared to the right. Therefore, the left one wins. And in this case, it would be that. Yes. Ah, okay, perfect. That's a very good question. And I'm glad you asked it. So we know that there's B has that, sorry, it's not B, but the blue one has a stronger electric field. So the electric field is just going to extend out more and push back the electric field from, come on. I can't believe it. Sorry, guys. I think my computer's stuck for just a moment. I'm going to give it some time. Draw it on the board. Oh, no, it's back, yes. So in this case, what's going to happen is you're going to have a stronger electric field that's going to be more dense further away from it, right? Because that's what a strong electric field is, like that. And it's always pointing outwards, okay? And this one is weaker, so it's going to go something like that. All right? Is there a region between these two that there is a zero electric field? Yeah, there is. I mean, we don't know the number for it right now, but it exists. It's somewhere around there. And at that point, the electric field is zero. All right, now we shifted it a little bit more towards the left. Yeah. If you put a positive charge right here, nothing would happen to it. All right. If I put it right there, it would get repelled. If I put it right there, it would get repelled that way. All right. But at that exact point, it would be good. Okay. Here I have a positive and a negative charge. What would that look like? How? Yeah, so it'd have a line going this way, or is it the other way? Which direction do I put my arrow? To the left or to the right? To the right, exactly. But it's like a magnet because there is more than one electric field line coming out of it. So you're going to end up with something like this. This looks like a magnet. Do you guys remember that? Okay. So the answer is 2 to the right. So far, so good? We did number 1 and 2 already, so I'm going to ignore 1 and 2. Ignore it. But answer for me number 3. It should be a pretty straightforward question. You're looking at the direction of the arrows. Someone tell me the signs of EFGHI, and this time it has to not be exact, please. Not because I don't want you to answer, because I want her to do an answer. Yes, Sabine. Exactly. E is negative. Negative. Everything else is positive. How did you know that? Direction of the arrows. Okay. Now, could you tell me which is stronger? Is it H is stronger or I? Which one has a higher charge, H or I? H. Gabrielle, you said H. Can you tell me why? Exactly. Two very good reasons. All right. So one, the arrows, there are more arrows coming out of it. All right. So that's one indication. And two, because it's actually shoving I's and G's arrows out of the way. So it's actually kind of in those areas winning against it. Right. So H or QH is greater than QG and QI. Okay. Now this one's a hard one. All right. Which one of these has the strongest electric field at the dot? All right. There's 4 options here. Which one can we eliminate right off the bat and why? Someone that's not Z. What I mean? B. Yes, you can eliminate this one right off the bat because at this point, in between 2 positive charges, there is no electric field. All right. So it's definitely not B. Yeah. Yes, you're right. So let me ask you a question. Let's look at this differently, the way we had looked at it before. what is the electric field on the dot, right? On this dot, what is the electric field on this dot felt by this positive charge here? To the left or to the right? Let me rephrase my question. I have a charge here, or I have a test charge here. At this point, if I put a test charge, right, which direction is it going to feel an electric field? Yeah? Margot says to the right. Is that what you said? What about, if we ignore that one, what about just this one? Also to the right, which means that there is a net electric field to the right. Okay? What about for this one here? It's going to feel, is it going to, which one's going to be stronger in terms of just magnitude? The electric field that it feels from plus or from the minus here, if I were to look at this point? The minus, why, Cedric? Absolutely, yeah, very good. So the minus is going to pull it strong, right? And the plus is going to push it weak, right? So overall, it's going to be not as strong as that one for its total electric, right? And the same thing applies for this one. So one of them is strong, the other one is kind of weak, so it's not going to be a, here, it's close to both of them, so therefore it's going to have a stronger electric field than all the other ones in this example. Yeah, you're right, the answer was I think this is two more examples. We'll just do one more and then I'll let you guys go. I think I'm pulling your teeth at this point. Okay, so we have 3-point charges. I'm asking you which direction is going to be the electric field. How would you do this? And then do it. Someone help me. How would you do this? Yep, sorry. Do you guys know about Adobe Connect? If I did that, would you guys use it? Adobe Connect is a program that publishes my screen to the internet. So on your computers, you can just go to a website and you can see whatever I see. Is that okay? You guys like that? I'll do that for next class, all right? So how do I do this problem? Draw that field line, so like the big glowing thing. That might not be very accurate because now we're dealing with numbers. All right, so if we're dealing with numbers, we're going to have to be as precise as we possibly can. What do we do for the last problem? How do we solve it? And can we use this method for the next question? Zach? Exactly. So, okay, so tell me, at this point here, what is the electric field felt by the charge on the left? By this charge here, by the -1 nanocoulomb. It's going to be going to which direction? Yes, you're going to have an electric field in that direction. What about from this negative charge in the bottom left? Diagonally downwards, yeah. Is it a strong one? Yeah, because look at it, it's -12 nanocoulomb. And is it what's it gonna feel from this charge here? Like what? Close to the, well, I mean, it's going to be directly opposite of this one that we drew. But now the question is, what is the net electric field? Now here's where we have to add up the 3 vectors using vector addition, right? You guys remember how to do that? Using vector addition to figure it out. But this is a multiple choice question. The options are all only A, E, B, C, and D. A, B, C, D, E. Which one could it only be? Only one possible answer. Gabriella. E, absolutely. Okay. E is the only one that's in the right direction. Because look, it's got a strong field in that direction, and it's got some weak fields that are kind of like this. This one's gonna make this one a little bit shorter, and this one is gonna make this arrow go up a little bit. That's why E is the only possible answer. If I were to ask you to calculate it, you'd be able to do that, right? I just need to give you what each of these squares are measuring. So if I said each of these squares is 1 millimeter, then you have everything that you need in this problem to be able to tell me quantifiably what the electric field is. There is a couple minutes left, but I won't do this question with you. I want you guys to just try it. I'll let you guys leave in 4 minutes, okay? Look at this problem, see if you have any questions. If you do, I'll be happy to answer them. At 25, you guys are free to. Thank you, thank you. I'll see you guys next Monday. Ask me if you have any questions for your quiz as well.